Thank you, Steffi, for the nice welcome and the introduction. Materials Reimagined. This is the title of our panel. And as Steffi said, there is obviously, and for the right reasons, a lot of criticism around sort of plastics, steel, cocoa. Think about it, 98% of the plastic that has ever been produced is still on Earth, and the other 2% were burned. So that's actually not the better solution either. We all know what burning plastic actually causes as a pollution. But obviously, and this is, I think, what is fascinating, and this is, I think, a nice bridge between, the deep tech and software and engineering we heard, today, and actually nature, right? And I think the impact, when you think about sort of applying technology and engineering in a very smart way, what we can actually, what impact we can create for a better planet. I think we have three great examples here on stage, and I'm glad that you're here today. Michael, to start with you, you actually have probably come, it's fair to say you have come the furthest from every speaker, I guess. Michael is actually based in Perth in Australia. Why don't you sort of introduce what you do and what the impact is that you create on a better planet with your company?
Yeah, sure. No, thank you very much, Christian. So I'm a co-founder of Uluu, and we're producing materials to replace plastic derived from seaweed rather than fossil fuels. And I guess in terms of the benefits that we provide the world, there are kind of three key benefits. The first is we tackle plastic pollution, and that's because we produce materials that are technically called PHAs that are produced by microorganisms through fermentation. So nature built them, nature understands them, and nature can break them back down again at the end of their life, so they're biodegradable. Yet PHAs have this really unique superpower in that they actually behave like plastic during use, and they give us all the properties that society has become reliant on from plastics. The second benefit is that we mitigate climate change, and that's because we use seaweed as a carbon source or a feedstock. So all materials require a carbon source of some kind, like the building blocks of materials. And rather than using hydrocarbons or fossil fuels, we use seaweed. And seaweed actually absorbs a lot of carbon dioxide from the environment, so much so that we can offset more carbon than we emit through our production process. And I think the final benefit is that seaweed is not only great for sequestering or avoiding carbon, but it also helps to restore our oceans. So you have huge issues in the world's oceans today related to nutrient pollution caused by industrial runoff and fertilizers. And seaweed is an awesome marine crop that actually uses those nutrients to grow. So it helps to clean the water as it grows, and it's a marine crop that we really want more of in the world, and we want to incentivize the scale up of seaweed farming through Uluu. Yeah.
You actually brought some samples with you, right, Michael?
Yeah, I thought it's like kind of nice to show sometimes what we're doing.
And I think it's so impressive when you look at what you can actually do out of seaweed, right? So this is the raw material, right? So what you produce.
Yeah, this is a pellet, and today there are 400 million tons of plastic pellets produced every year, all using fossil fuels. And we are producing Uluu pellets to replace really the petrochemical companies upstream in the supply chain. And these pellets can be processed using existing plastic manufacturing equipment and really converted into products across the key verticals that plastics are used today. So, for instance, we have an injection molding grade pellet, and injection molding is one of the key manufacturing processes. And here we're focused on replacing rigid plastics in cosmetics packaging to begin with. So this is just an example of a cosmetics jar and the lid replaced with our materials that behave and really function just like plastic.
And that's a lid that is fully compostable, right?
Yeah, so you could put this in your home compost in contrast to an industrial compost, and it will biodegrade in a few weeks. If you really chop it up and increase the surface area, it may be a few days. So it's quite magical. And then I guess just the other product that we have is a fiber grade pellet. So as you may know, over half of our clothing is made of plastic. And that's a huge issue when you wash your clothing and you breathe in, these microplastics that get into everything, essentially. And here we have a pellet that can be melt spun and drawn into yarns and knitted and woven into textiles with similar properties to polyester, which is very common synthetic textile, without obviously those microplastics, because it's a natural biocompatible material. So that's the other market that we're starting in.
Fantastic. I mean, it's fascinating when you think about it, right? And I think you even have a film with you, right? Or a very thin sort of plastic that you use typically for packaging.
Yeah, so I think this just shows the versatility of PHAs.
Yeah.
And yeah, we can also turn them into films. These are obviously more commoditized, price-sensitive markets, and but it's a nice demonstration of just what's possible with natural materials. So yeah,
So there's nothing wrong with plastic, right? If you basically produce it in the right way. And I think the same is true for Christoph, for you, right? And why don't you sort of introduce what you do, what the innovation in steel is today, actually?
Yeah, no, indeed. And unfortunately, I wasn't able to bring a nice steel bar, but maybe
understandably.
I guess we have enough around us as well. Indeed, Stegra, formerly H2 Green Steel, I'm still going to use this name for the last time, and then I'll not use that again. But that's just been a brand which I think has been known quite widely. We have a project in northern Sweden, and the key for us was, and the vision from the very beginning was to, abate hard-to-abate industries, and steel is obviously one of the key industries that needs to change. It's accountable for between 7 and 8% of global CO2, so it is fairly significant. The key for us is that we don't and we can't change the end product, so we are always going to need steel. So what we have to look at, similar to what Michael just described, is how to get to this point. And the key in the steelmaking is the reduction of iron ore. And this was typically done with carbon from coal. That's typically the process. What we are doing is we are reducing iron ore with hydrogen. Green hydrogen, therefore northern Sweden, because obviously the key for us, for the entire process, is to have access to reliable, renewable energy. That's the basis of the process, effectively. The rest of the process in itself is not necessarily novel in that sense. It is proven, it has been proven for over a decade, not with green hydrogen necessarily, but we can replace the hydrogen used with green hydrogen. So it is just applying what is available in terms of technology at the right location, where renewable energy is available, and the output is entirely unchanged, is steel. And
with the same specifications,
same quality. So that's the beauty. So also from an end user perspective, we've just also heard that in the previous panel, that's obviously the key starting point, and that was also the key starting point for us. The beauty is that, if we sell to BMW, the same coil will arrive, but it will be a green coil, whereas maybe the week before it would have been a brown coil. So they don't have to change any of their processes, or any customer wouldn't have to. So that's where, from an end use perspective, is really, really beneficial, and has allowed us to create a market where there is a value and a green premium associated to our steel compared to existing steel production.
But when you think through that, that probably means that the steel industry in Europe will also relocate, right? So move more to the north and to the south, where you have a surplus of renewable energy. Because
yes.
historically it was more located near to coal mines. Is that?
That is, I guess, a very fair statement. So the key input is changing from coal to green electricity, to renewable electricity. Therefore, yes. I think the process, obviously, that I just described, is the reduction of iron ore is one step in the process, and then there is all of the downstream industry that is existing in Europe, and not least in Germany, that may be part of a transition where the first part of the production, i.e. the green iron, is done elsewhere, and downstream is still done where it's done today. There's various ways of looking at that, but yes, that could be one outcome of this transition, yeah.
Oh, wow. Sara, coming to you. You have been, working hard with actually your brother, the two, who founded the business, on making sort of the cacao, supply chain. I think across the entire ESG sort of component, much more sustainable and less exploitative, right?
Yes. So we produce cocoa-free chocolate. When we started the company 3.5 years ago, we learned that cocoa is endangered by climate change, and that maybe we might have a problem 10, 15 years from now, or not we, but like the multinationals, Mars, that there's not enough cocoa. And so this was the starting point for our business. And what happened in the last year alone, climate change endangered cocoa quite a lot. Prices are sixfold as they were before. And in the food industry, margins are quite small. It's not like software as a service or like 50, 60, 7% gross margin. It's more like 5 to 7. And so if the ingredient is sixfold as expensive, like there's a lot of companies that have existential pressure, especially the small and mid-sized ones, and so they go into bankruptcy. And so basically when we started, we didn't know all that. We thought that we have a solution for 10, 15 years from now, and now we're in the midst of a storm, that our cocoa-free chocolate is basically not just because of the ESG, because of the CO2, but just because we save a whole industry with an alternative to chocolate. We don't start, or we never started to replace or wanted to replace chocolate as such in total. So yeah, it's more sustainable, less CO2, no child slavery, it's very supply chain stable, no volatility. And you might wonder how you do that. So I myself, I'm a food chemist. I studied here in Munich. And what I learned is that 80% of the flavor and what we love in chocolate and cocoa comes out of the processing. So the fermentation, the roasting, and then the blending with sugars, milk powders to chocolate, and not so much from the cocoa bean itself. And so we translated this analogy on sunflower seeds. So there's plenty of sunflower seeds in Europe, very short supply chains, 45 million tons, way more than cocoa. And we process those in the same way as cocoa. So we ferment them, roast them, grind them, and then turn them into a chocolate alternative that we supply as a B2B ingredient provider to the industry, to confectioners, to large multinationals, and they make products.
Yeah. I mean, that's actually a good point, Sara. But I think what the three of you have in common, that you are producing raw materials, right? You're not trying to build a consumer brand and compete sort of with the big global brands out there, but you're basically positioning yourself as a supplier of raw materials. But still, Michael, I think the question obviously is, now that we have seen what is actually doable and feasible, but how can you actually make this scale? Is there a chance that you can, with that approach, and probably other companies around sort of the globe will try the same thing, can you, as a sort of alternative in general, replace the entire fossil plastic that is actually needed?
Yeah, I genuinely believe that we have a model that can scale to replace plastic. And I guess that's, we started as a company with that mission, and we selected PHAs as that material to replace plastic because of those properties, but also the versatility in those properties. So plastic is this cloud of different types of polymers, synthetic polymers, and PHAs is a cloud of natural polymers. And so we really believe that PHAs can replace many, if not all, plastics. And then you need a feedstock that can actually scale to replace fossil fuels. And seaweed can do that without competing with arable land, or it doesn't require fertilizers or fresh water. It gets everything it needs from the sun and the sea, and can actually generate positive externalities as you scale it up. So
there's enough seaweed available to scale in theory.
Yeah, in theory. So today, we have enough seaweed on market that we can build the first kind of handful of large-scale commercial facilities, but we do need to scale up seaweed farming by a couple of orders of magnitude to get to that level. But the potential of seaweed, not just for what we're doing, but for many industries, is so significant that many forecast that seaweed farming will naturally increase just due to the benefits of that. So we're confident. Yeah.
What percentage of the surface of the ocean is actually then sort of needed or covered?
Yeah, so it's about 0.1% of the ocean surface area that would be required to farm seaweed to replace the fossil fuels used to produce plastic today. And you look at like the Great Pacific Garbage Patch, which is off the coast of California. That's about a third of the size of the Great Pacific Garbage Patch.
Oh, wow.
To put it in context. So it's not trivial, but it's not unrealistic. And Indonesia, for instance, today is the world's second largest producer of farm seaweed. And them alone, in terms of the capacity for seaweed farming in the right environments, they could produce more than half of that total seaweed that's required. So to become like the Saudi Arabia of seaweed, yeah.
Oh, wow. And Christoph, when we're sort of coming to you, how obviously, I guess it's quite, capital intense what you're planning to do. How are you tackling the issue of sort of building production facilities?
Yeah, I mean, I guess the first point, the crucial aspect in order to scale is grid capacities, renewable electricity we talked about, but it is power availability as well. Even if the location in northern Sweden is fairly unique in that sense, the grid has limits. So you cannot just replicate that indefinitely, and even more difficult in other locations across Europe. So we are looking at different projects across the globe, and there's a few spots that certainly will be better than others, and there is other areas in Europe we are looking. Portugal, for instance, you mentioned the south, I think that's an obvious one.
Yeah.
Canada and Brazil are other areas that just make sense, availability of iron ore and hydropower, which is obviously highly beneficial. The capital intensity is the second challenge. So our project, the cost is a total of 6.5 billion euros. That is something that we can, as a startup, cannot always just replicate. That's going to require partners. That is going to require new models. To your question from earlier, is potentially requiring the industry to also slightly reinvent itself, which means that the downstream facilities and the special production of very very specified coils might have to invest in a project together with us. Just to make an example, I think there's going to be an involvement of how the industry is going to have to think about these huge investments, because obviously we are in this first phase are going to produce 2.5 million tons of steel. Europe is over 100 million tons of steel. The market alone is obviously huge.
Yeah.
So it's going to require quite a few of these projects.
And how much have you? I mean, there was a lot of talk today. That obviously deep tech requires a lot of capital and is quite difficult to raise here in Europe. How much have you raised so far?
We have raised a total of 6.5 billion basically to fund the first project. So that is under construction. First production is 2026. To be able to raise that amount of capital, we obviously required many partners to come together, many stakeholders to come together. Including off-takers, including OEMs, including European banks, export credit agencies, the German government through Euler Hermes supports the project. So there is the requirement for many parties to come together.
It's actually, but it's great to see that it's possible in Europe, right?
It is possible. Yeah, it is possible.
Well done. 6.5 billion in the first go. Sara, coming to you, how are you planning to scale?
So we are already kind of like slightly scaled. We have 70 people. We have our own production facility, and we produce for like a number of threshold, like 25 to 30 tons per day. So trucks coming every day. The issue with scaling is the operational excellence. You have quality management, you have supply chains, logistics, and besides the access to capital, the excellence is the other difficult thing to master. In the end, we are producing food. It has to be safe. It has to be safe for babies, for elderly. So to do this every day with every single gram you produce, that's the true challenge for us. And we started by being in the facility ourselves, actually really sleeping under these machines because we didn't have staff in the beginning. It's quite hard to find blue collars that run facilities, basically. So that was really burdensome. But yeah, access to cash is the other thing, right? As you said, deep tech, steel is quite expensive. Yeah.
Well done. We are running out of time, but maybe we should, in 2 years' time, we should, do the panel again and see where you are and where you have come. Then. So thank you so much for coming to DLD to Munich, and best of luck.
Thank you
so much.
Thank you.